In this video, I'm going to talk a little bit about Unit 2, Part 1, Lesson 3 of our college algebra class. And this is where we discuss about average rate of change and give you a preview to the calculus concept called the difference quotient. Now, I hope to explain this in more detail and clarify any misunderstandings in class, but in general, let me just summarize this real quick. Rate of change is another fancy word for slope. And when we're talking about linear equations, if I had a linear equation represented by this graph, its slope is consistent no matter where we look. If I take a look at this point or this point and calculate the slope between those two, I'll have some slope. We'd have a rise and a run. We can calculate the slope. Now, if I pick this point and another point and calculate the rise and run, while the numbers themselves might be different, the fractions created, or the decimal result, when simplified, would be exactly the same. As we move on in our mathematical career, we're going to start encountering curved lines, and we would like to know what the slope of a curved line is. So here I've got this curved line, and I'd like to find the slope of that curved line. And I could find the slope of that curved line by picking two spots at random, or specifically, it doesn't matter. We can pick two spots and calculate the slope between them. Now, the slope between those two spots is what we call an average rate of change. We call that an average rate of change because it is the rate of change between these 2 points. And this green straight line, if we were to calculate its slope, its rise and run, that would give us an estimate as to how steep this black line is over that distance, over that horizontal distance. But if I was really focused at this point P, and I wanted to find exactly how steep this curved line was at point P, well, this estimate might not be very good. And so I might choose two other points that are a little bit closer. Let's say I take this point and this point instead and calculate the slope of the line between it. Now, the slope of this green line is a little bit better than the first one, but it's still not exactly the same as the slope precisely at this point. So the argument again may be to pick 2 points that are closer still. And so if I could pick these 2 points and draw a straight line between them and calculate the slope. And again, I'm getting a little bit better, but still not quite perfect. The best way to determine the slope at this point P is essentially to pick 2 points and sit them on top of one another. Reduce the horizontal distance between them until there is no more horizontal distance. Then those 2 points would represent coordinates that I should be able to find the slope between, and that would give me the precise steepness of this line, or this curve, I should say, at that particular point. But hopefully you recognize that that would be a problem because if the 2 coordinates were sitting on top of one another, we wouldn't be able to use our traditional slope calculation. And that's what this is back here reminding us. M, meaning slope, of what we call a secant line. A secant line is a straight line that strikes a curve in 2 points, just like this average rate of change we were just talking about. The slope of a secant line is the change in y divided by change in x, and undoubtedly you've seen this in your algebra classes as this, y2 minus y1 over x2 minus x1, where x1 and y1 represent a coordinate. Let's say this position might be x1 comma y1, and x2, y2 represent another coordinate. Let's say that this one was x2 comma y2, and by subtracting the x's we can find the change in subtracting the y's we can find the change in y's, and subtracting the x's we can find the change in x's. Sometimes we mark that with a delta y or a delta x. And so this delta notation is pretty common in science classes where we talk about the change, delta, the change in y over the change in x, using the delta terminology. But as we look at this in a calculus perspective or college algebra perspective, we'll use function notation to identify these terms. Instead of using x and y, we're going to use f of x and a modified form of it. And this is a little bit tricky to understand at first, but once it starts to make a little bit more sense after it's explained and shared with you a couple times, I think it'll become a little bit more clear. But let's look at these two coordinates again, and instead of identifying them as x and y, let's take a look at P here for a second. The x-coordinate, the position along the x-axis, of course, is going to be x, but the y-coordinate associated with it, we're not going to call it y, but we're going to call it f of x. So here we have a coordinate x and f of x. So if I'm thinking of my slope, slope is equal to y2 minus y1 over x2 minus x1. Let's consider this our first point. So we've got y2 minus y1. So this f of x is y1. And we have x2 minus x1. And our first x we're just calling x here. Now this equation, and this is called the difference quotient equation, this is saying that, okay, let's just scoot over some horizontal distance. H is arbitrary at this point. It can be any number that we want, but we would like for it to be pretty small to get a good estimate. We're going to scoot over some h amount. Now, scooting over some h amount would be the same as starting at this x and simply adding h to it. So the new x-coordinate of this point is not x anymore, but it's whatever x plus h is, the sum of x and h. And therefore, the y value associated with this position is not just f of x anymore, but it's f evaluated at whatever x plus h was. And so this slope of our secant line is represented by this equation, and it's just a modified form of the slope equation that we've seen so many times in the past. But what's particularly helpful is to see that, well, this denominator simplifies a little bit, and it becomes this particular expression. So if I wanted to find a slope of a curved line at any specific point, at an instantaneous point in time, I would pick two locations and reduce the horizontal distance between them to be 0 if possible. But here again, we can't use 0 because of the division by 0 at the bottom of this denominator, bottom of this fraction, and we need some calculus techniques to handle that. We're not going to spend much time talking about the calculus techniques in this video, but that's ultimately where we would go and why our skills in pre-calculus or college algebra are going to be pretty important for us. So in this portion of the notes, we kind of already did this. I established this secant formula. This secant formula represents the difference quotient or the slope of a secant line. So that whole conversation that I had in the video was really meant to complete this question right here. But we could add these two vocabulary phrases if you're not already familiar with them. This phrase secant, as we've talked about, represents a line. A secant line represents a line that crosses a curve at 2 points within a small window. A tangent or tangent line, on the other hand, touches a curve at exactly 1 point. And it's this secant line that gives us an average rate of change, whereas a tangent line, something that our calculus students complete, would give us what we call an instantaneous rate of change. So for now, we're going to live in the world where an average rate of change is going to be good enough for our purposes, but in the future or eventually we're going to be calculating instantaneous rates of change. And in this example, we're going to try to simplify the difference quotient for two different functions. We've got 1 and 2 here. You may have noticed that the difference quotient definition is slightly different for part B. Let's not worry about that form. We'll use this form for part B as well. So let's try part A for just a second. Now in part A, we need 3 parts to the difference quotient. We need f of x plus h, we need f of x by itself, and we need an h. So before I even simplify this, I would like to find out what f of x plus h will look like when simplified. And if you remember, f of x is just 3 times something squared minus that something. So the way I like to evaluate these is I like to change the letter x to a set of parentheses. And inside the parentheses, I'm going to substitute this expression, x plus h. And it's worthwhile to simplify this ahead of time because we can do this away from the fraction bars, and that's going to help us, I think, perform our work a little bit more clearly. So all I'm doing in this first line is expanding that squared binomial, and now I'm going to FOIL that binomial. Multiplication is commutative, so we can do this in a slightly different order instead of left to right. So I have x squared from this distribution. On the outside I have an x times h, and on the inside I have another x times h. So we have two x times h's, and then for our last term we've got h squared. At this line I'm going to distribute, and we're left with 3x squared plus 6xh plus 3h squared minus x minus h. Because not only does this 3 distribute into this group, but this minus sign distributes into that group. Okay, so this is what f of x plus h looks like. Now let's simplify the difference quotient. The difference quotient said we needed the f of x plus h component minus the f of x component, all divided by h. Well, here again, f of x plus h is, this thing here is just the same as this thing here. So I'm going to rewrite this in the fraction, and it's going to get a little bit messy for a moment. 3x squared plus 6xh plus 3h squared minus x minus h. Okay, that component takes care of f of x plus h. From that, we need to subtract f of x. Now, f of x was our original formula, our original function, 3x squared minus x. Oops, 3x squared minus x. And in the denominator, we have just the expression h. So let's simplify. The difference quotient can be simplified, and this happens quite a lot. There are often going to be many terms that will cancel in this simplification process. Now you can drop the parentheses or grouping symbols here in the first group, and in the second group we would distribute this minus sign. So we have a minus 3x squared, and then after we distribute, this becomes a plus x. And mentally, I think you can do this work. You don't actually have to rewrite it a second time, but you'll notice that this 3x squared at the beginning minus 3x squared towards the end is going to reduce to 0. This minus x plus this x is also going to reduce to 0. We have nothing else that will simplify in the numerator, so I'm just going to write it down and see what's left. 6xh plus 3h squared minus h over h. That's already a whole lot better, but we can still clean this up more. There is an h that's common to each of these three terms in the numerator, so I'll factor it out, and I'm left with 6x plus 3h minus 1 divided by h. And now hopefully you recognize that this h can cancel with this h, because these two terms in the numerator are separated by a multiplication sign, and in the denominator we have h separated from the number 1 by a multiplication sign. When terms are separated by a multiplication sign, we can cancel across the division bar, across the fraction bar. Now we're left with a difference quotient, simplified to be 6x plus 3h minus 1. And the benefit to having this difference quotient reduced is that it allows us to calculate the slope of the tangent line at any point x, with h equal to 0. We can now specify our horizontal distance between some point x and some other point next to it with a horizontal distance of 0. We can do that now because this equation allows for an h value to be 0. It doesn't give us an unusual result where we would have to divide by 0. So this answer in the box is the simplified difference quotient for part A. This was our answer for part A. Let's go ahead and try part B. Remember, f of x was defined as x cubed. And before we simplify the difference quotient, we're going to need to establish what f is when evaluated at x plus h. So what does x plus h cubed look like? Pause the video now and try to expand this on your own. Resume playback in a moment to check your work. There was a fair amount of algebra necessary to simplify f evaluated at x plus h, but I think this is a good result if you made it to this point. Well, now we can simplify the difference quotient. The difference quotient requires f of x plus h to be recorded first, so I'm just going to write that here in its simplified form. X cubed plus 3x squared h plus 3xh squared plus h cubed. So there's f of x plus h. From that we subtract f of x, which we know as x cubed in this problem. And then finally all of this is divided by the value h. Again, we're going to get some items that cancel, but in this case there's only one. This x cubed and this x cubed will cancel after simplifying the numerator. And in the denominator, in the remaining numerator, we have 3x squared h plus 3xh squared plus h cubed divided by h. Again, we have a common factor of h in the numerator. And with that common factor in the numerator, h, can factor or reduce in the denominator with the h, and now we're left with a simplified difference quotient of 3x squared plus 3xh plus h squared. So that seems like a lot of work to complete for a problem like this, and it is. But part of getting you ready for a calculus class is to make sure that your algebra skills are very, very strong. And this is one of those instances where having a very strong algebra skill set will help you immensely when you enroll in calculus. If you have further questions, please let me know. Otherwise, thanks for watching.